I introduce our guest speakers, I'd like to do a quick overview of the importance of water and why companies, investors, customers, and governments should be very concerned about water and our water use. First, let's review the basics. Of all water on Earth, only about 1% is usable by humans and other living things, meaning that there's 99% that's not. That 1% of fresh water is stored in our soil, groundwater, lakes, rivers, and streams, swamps, such. And if global warming increases, this tiny limited resource will be in high demand. And with new greenhouse gas reporting regulations, governments, corporations, and investors will need to address their water use related to climate financial risk, their net zero targets, health issues, as a natural capital asset, and more. Some see this as a daunting challenge, but our Stanford professor, Will Tarpeh, who teaches the EIT 120, the role of water and energy for circular economies, sees wastewater as an opportunity for circular economy innovation and the creation of new businesses. Well, with that ground setting, I'm excited for you to spend this time with Professors Will Tarpeh and Will Chueh. To start, Professor Tarpeh, would you please describe the R. Buckminster Fuller quote you refer to when describing what you do?
Absolutely. Thanks, Anita. And thanks, everyone, for joining today. Yeah, there's this quote from R. Buckminster Fuller. I'll paraphrase it, but in short, it has to do with pollution. We consider things pollution because we're ignorant of their value. If we think about this one chemical compound and change where it is and what it's around, we might call it a product rather than a pollutant. So a perennial example of this is something like ammonia, which is a common fertilizer component and feeds over half the world, arguably. However, when ammonia is present in wastewater, we consider it a pollutant. Ammonia hasn't changed anything about itself, its bonds, anything like that. But simply by resituating where it is, we can turn pollutants into products. So that motivates a lot of the work we do in my group, and that's featured in the course as well.
Great, thank you. Professor Chueh, do you have some questions for Will? This is going to be fun. Will and Will, do you have some questions that you would like to pose?
Absolutely, Anita, and it's great to be on stage with you, Anita, and of course with Will. Before I ask Will some tough questions, I just want to give everyone a sense of the scale and urgency of the challenges confronting us on energy and sustainability. We have 8 billion people on Earth, and whatever we do will have to be delivered to the entire population. So that gives you a sense of the scale. In terms of the energy transition, estimates from Stanford is now putting this at approximately $70 trillion in total. So this is a huge economic opportunity for the world. And then finally, the urgency. The latest projections are showing if we don't alter the way we use our energy today, we only have about 7 more years until we reach the 1.5 degrees Celsius temperature increase, and a little bit over 28 years until we've reached the 2 degrees Celsius temperature increase. So this gives you a sense of the scale and the urgency of the challenge in front of us. So this is really what we are trying to tackle here at Stanford, across the entire university, and especially in the Dorr School of Sustainability. And in the Energy Innovation and Emerging Technologies program, we're covering many aspects of it. And today I'm really delighted to talk to Will about water. So Will, when we think about water, we think about maybe water for drinking, water for food, maybe also water for, say, electricity generation. But water is a lot more than that. So I really want to sort of pull the threads on here a bit. And maybe firstly, have you talk more broadly, what are some of these connections between water, water treatment, and also energy? What is that connection there that maybe not everyone sees from daily life?
Right. Yeah, great question. Well, there's some really fundamental connections between water systems and energy systems. As you mentioned, water is used a lot to produce energy, as it were, in hydropower, and that's maybe some of the oldest incumbent technology that connects or is a sinew between water and energy. We can also think a lot about energy in terms of the energy that goes into treating water, to producing drinkable water, as it were. And with that energy comes a lot of greenhouse gas emissions as well in terms of the environmental context. So some estimates put nationwide in the US, wastewater treatment plants are responsible for about 3% of our total energy emissions. So of course, that's a small percentage, but a huge number, right? So just treating wastewater so that we can emit it and treating drinking water so that we can drink it costs us a lot of energy and associated emissions. So in any effort we can take to lower the energy input of treating water, that's time well spent in terms of these transitions. Water is, of course, used a lot in chemical manufacturing as well. So when we talk about electrifying manufacturing and reducing the environmental impacts of manufacturing, water is going to play a huge role there, especially because we often discharge water from industry into the environment. And if there are ways to capture value from that water, we can reduce the total energy input and emissions associated with chemical manufacturing.
So Will, you mentioned that wastewater treatment accounts for 3% of our emission in terms of carbon intensity. Just for everyone else, this really sort of is on the same scale as aviation. So when we think about decarbonization, these 3% really add up. So aviation is a huge carbon producer. So likewise, from Will's work, this is also highlighting the importance of wastewater. So Will, how are these carbon generated, the CO2s and the emissions in the wastewater? Is it from the energy generation, or is it from direct byproduct of water treatment? How does it interact with the environment?
Yeah, when we're treating water to drink or treating wastewater to emit, one of the biggest things we do is we add a bunch of oxygen to that water to drive biological processes that will consume all of the dissolved carbon. And I mean, our ideal product there is actually, believe it or not, CO2. And so that's where a ton of the direct emissions come from water treatment plants. And also adding that oxygen takes a lot of energy itself. So aerating that oxygen, aerating the wastewater or water that we want to drink can cost us around 50% of the energy associated with treating water. You can also imagine all of the pumping that has to happen from across a whole city, say, example, to pump millions of gallons of wastewater to one place costs a lot of energy. And so there's movements to think about what does it look like to treat water on site in a building, so you don't have to transport it miles and miles before it gets treated. A third area where there's a lot of energy involved in energy and emissions, in particular, involved in wastewater and water treatment, is actually kind of hidden. It's embedded in the chemicals, with the chemical inputs we use. So if we add hydrogen peroxide, or if we add chlorine, or add an acid or base to clean up our water, if we think about that from a life cycle approach, like what went into producing those chemical inputs that we're using to clean the water, we've seen examples where something like making sulfuric acid can be 70% of the emissions, the carbon emissions associated with a specific treatment process. So it's kind of like there's surface level emissions, direct emissions, and then you have to dig all the way down to, we would call them scope 2 or scope 3 emissions associated with water treatment as well.
Wow, it's really quite intense in terms of the carbon footprint. So the carbon footprint of the energy needed to treat the water, the carbon footprint in terms of the oxidized product from treatment, and also the carbon footprint of the chemicals used in treating the water. And that's what amounts to the 3%, Will, that you talked about.
Right.
What are some of the exciting innovations, whether it's at the technology level or at the systems level, that you are pursuing to decrease these carbon footprint?
Yeah, I think even in addition, maybe just even before decreasing them, just to track them, I kind of laid out what happens with CO2, but we can also think about methane emissions, and increasingly we're thinking about N2O, nitrous oxide emissions as well. And believe it or not, the answer, at least of the experts I know, myself included, is we don't know how much N2O is emitted or methane is emitted at treatment plants. So there's a huge movement right now to just be able to track these emissions, and so that we can get the pieces of the pie and know where we should cut things down. But in terms of decreasing emissions, so one aspect of decreasing emissions is monitoring them. So there's a need for these high resolution sensors to be able to measure these directly from water treatment. But some of the innovations we're looking at are just ways to establish circularity, right? If we can reuse an acid or base, or can we generate it electrochemically? we're doing a lot of work kind of taking electrolyzers and fuel cell type of architectures and saying, can we use those not just to generate oxygen and hydrogen, or to use oxygen and hydrogen to drive energy storage, but can we actually use those to treat the water and replace chemicals with electricity? So we can produce acid and base when we do water electrolysis. Normally those are seen as byproducts because you're focused on the gas. We sort of flip that and say, let's treat the gases as byproducts and treat the protons and hydroxide ions we make as the real valuable product. And if we have pH gradients, then we can start to do things like regenerate ion exchange resins that help us treat water, or we can wash reverse osmosis membranes with acid and base. So we can literally just look all around chemical manufacturing and water treatment in particular and say, anytime you add an acid or base, we can generate it on site using electrochemical techniques, just using an electrolyzer that's adapted to water treatment. So those are a couple innovations that we're working on right now, but maybe more specifically in terms of a circularity case, we're doing a lot of work these days on trying to recycle lithium as we think about ways to affect chemical manufacturing. And nitrogen is another case, but we can talk about those in more detail as we go.
Thank you. Well, this will be a great segue for my next question, but maybe one more question on the current point. You know, wastewater treatment has been around for a long time. Can you give us a sense of the degree of innovation that we have seen, say, over the past 50 years? Is this a field in which technologies are constantly being tried and tested, or is this sort of ripe for innovation? Give us a sense of what is the status of innovation?
It's a super interesting industry. So, I mean, wastewater treatment plants were generally, most of them built in the early 20th century, so about 100 years ago. And their main benefit was reducing diarrheal disease. So people were not experiencing things like cholera or dysentery in the US anymore, or to as nearly as large an extent, because we were chlorinating drinking water. We were treating our wastewater. And so the big innovations have been, how do we remove pathogens, disease-causing organisms from our wastewater so that they don't infect other people? Then came along innovations like, how do we get all of the organic matter out? And that's how we oxidize it. And so then we've sort of, kind of like oil and gas refining, we've started adding on unit processes to do additional things. So now we're able to treat nutrients like nitrogen and phosphorus, and we're able to treat emerging contaminants. You may have heard of forever chemicals like perfluorinated chemicals that are just being regulated now. So it's kind of like we keep adding on. But in terms of innovation, I think the key innovation areas right now are we're used to removing pollutants. That makes a ton of sense. And the key innovation right now is, can we remove pollutants and do something useful with them? Can we remove and recover them for some valuable input elsewhere? Right now, if we think about like how much money we're kind of flushing down the drain, it's in the order of billions of dollars, is if you think about the dissolved chemicals that are in wastewater that gets emitted into the environment.
So, Will, this is a great segue. So walk us through a little bit how these valuable chemicals entered the wastewater to begin with. So you mentioned lithium, which is used in batteries. You mentioned nitrogen, you mentioned ammonia. So just walk us through a little bit about what comes in, and then what do we want to concentrate out of the wastewater?
Yeah, there are lots of different types of wastewaters, which is kind of where we start on step one of or module one of the course, this EIET course. But broadly speaking, if you think about a household or a business, think about your house and everything that you do that goes down the drain. There's going to be nitrogen, there's going to be phosphorus, carbon. All of that can be recovered. It's not recovered now, but it can be reused, right? The challenge is to be able to separate it out of the wastewater and make something valuable from it. Now think about if you work at an industrial company, right? Say you're manufacturing batteries. There's going to be battery scrap on the floor that you're going to have to get rid of. You're going to use acids and bases to leach or to precipitate at different stages. And you'll have some wastewater that you generate as a company that you will deem a waste and also send to a wastewater treatment plant. So wastewater treatment plants get these huge amalgamations, mixtures of everyone's waste products. And their job is to sort of do the equivalent of solids recycling, where you say, okay, the plastics go here, the metals go here, this type of thing. But you'd have to do that with different elements. There have been some estimates looking at like transition metals, like we're talking like gold, silver, that's in wastewater as well, from the medicines we take or from mining tails, et cetera, mining tailings, et cetera. And this is also on the order of tens of millions of dollars that's deemed waste simply because it's too dilute, going back to the Buckminster Fuller quote. But if you can change the concentration or change its purity, then we have a product again.
Will, give us a sense, for every, say, kilogram of batteries I have to make, or better yet, a kilogram of battery I have to recycle, how much water do I need to supply to that process? Just give us an order of magnitude estimation.
Yeah, for a kilogram of batteries, you're looking at easily hundreds of liters of water, right? Or hundreds of liters or gallons of water. And so the water use is something we've analyzed, and it's an environmental impact that we don't look at as much as, say, greenhouse gas emissions or carbon intensity. But it scales quite fast. So if you think about the scaling curve we need for lithium-ion batteries, or let's just say renewable batteries, the scaling curve for water is 100 times higher in terms of liters needed. And a challenge with that is that across the world, over 80% of wastewater generated is not even treated before it makes its way to the environment. So we're just letting it all go, and then we're saying, oh, we're scarce, we need more lithium, but we actually just let it pass by, right? Because it was in too dilute a stream for us to consider valuable.
Yeah, I mean, this is a tremendous number, Will, because if you consider the amount of materials we have to make, say, for electric vehicles, all of the utilization on the order of megatons, a million ton per year per material. And then I think, Will, you just told us you will need something like 100 liter per kilogram. So the amount of water used is just tremendous. Right. And then you're also now telling us that in addition to the water intensity, there's also the issue of useful and expensive elements which are dissolved in the water that you will have to separate out. And unlike recycling, you couldn't just mechanically isolate one type of plastic from another. There's no label. There's only elements and chemistry. Right. So maybe moving into that a little bit more. So what, give us a sense sort of at a high level, what are people doing now to separate the lithium from the cobalt? And what can we do to make that process more efficient, less carbon intensive?
Yeah, a lot of the ways that we're separating out lithium and cobalt have to do with mining processes, right? And it's interesting because water is also used in mining. And so you could argue what we're doing is kind of innovating on mining processes as well, right? And so in general, what people are doing is they usually break this into kind of 3 types of recycling processes. There's mechanical, like you mentioned, you need to separate the battery parts if you're starting with a spent battery. There's hydrometallurgy, where you, like the name suggests, you put it in water, specifically acid, and you leach out all of the elements and they dissolve in the water. So that's where I spend a lot of time thinking. And then there's pyrometallurgy, where you use energy basically to carbonize to pyrolyze what's in the batteries. And so a lot of this hydrometallurgical processing is in fact exactly what we do in my group. It's taking a water stream and saying, how do I separate the elements out here? Broadly speaking, what's done nowadays is dissolving the water out, so boiling the water off, or trying to precipitate a solid out. What we're bringing to this conversation is, can we use kind of water treatment methods, if you will, things like membranes that are selective. They let some ions through and reject other ions, or things like adsorbents, like a filter bead that does the same thing, is selective between different ions, that allows us to produce higher value products while doing so at lower energy inputs. It takes a lot of energy to boil water. It takes a lot of energy to remove a solid from a liquid. In terms of precipitating, it can take less energy to just flow water through a membrane and get selectivity, given the features of that membrane. So that's a lot of our work these days.
So this would be a sort of a souped up version of water purifiers we use in residential applications.
Yes, yeah. So the analogy I make often is it's like a Brita filter. And if you've ever been curious or accidentally broken open a Brita filter, you would see a bunch of black beads. We are designing those black beads, but rather than just take everything out of the water, we design them to just take lithium, or just take cobalt, or just take nickel. And if we do that, then we can make a really high concentration, high purity lithium stream, or cobalt stream, or nickel stream later.
Wow, Brita filters for lithium. Sounds very exciting. Will, we talked a little bit about industrial applications of wastewater and purification to recover precious elements. But how about agricultural or residential applications? You alluded to ammonia. Talk us a little bit about how fertilizers, residential gray water treatment, how does this come into the equation?
Yeah, there's a lot you can recover from wastewater. One of the things I like to say is the easiest thing to recover from wastewater is water. And so one of the things we can do from gray water, think your shower, think water besides toilet water in your house. You can recover water from that because it's actually quite dilute in other contaminants. So we can put it through something like reverse osmosis, for example, and get just water out. And some people have those types of recycling systems on their properties. In terms of nitrogen, that's a fascinating case to us because it's contrasts a lot of ways with lithium. Lithium is an economic case, right? There's a drive for lithium, but we don't yet know the environmental consequences of lithium discharges into the environment. But we know that most people would say, no, I want that lithium, especially if they happen to be related to the battery industry at all. Nitrogen is kind of the opposite. There's a bunch of environmental data about algal blooms and dead zones, oxygen limited zones in water-based environments that nitrogen can really cause havoc for. But there's not that strong economic case yet. And that's because we have a wonderful way of manufacturing fertilizers, the Haber-Bosch process, that's cheap, it's relatively energy efficient, but it also emits a lot of CO2, in part because of how we produce hydrogen nowadays. But in any case, what we're trying to do is use wastewater from fertilized fields, from municipal wastewater from our homes, and that contains a lot of nitrogen. If you collected all the fertilizer runoff and all of the municipal wastewater around the world, not an easy task, but if you did it, you could offset around 25 to 30% of all of the fertilizer needs of the entire world. So that's basically where we're letting a quarter of what the fertilizer we need go down a drain or go into waterways. So we are designing electrochemical techniques to be able to select just nitrogen out of complex real wastewaters so that we can make fertilizer on site, which can also increase access to fertilizer across the world.
Will you touch upon circularity briefly in all three cases? Can you give us a few examples, maybe sort of industrial and residential examples of where circularity has been achieved, which we don't have to sort of make new chemicals or mine new things from the ground to sustain our lifestyle? What are some of the examples at work?
Sure. A great example is actually going back to reverse osmosis. So most of the time we think about making drinkable water from seawater, that's what reverse osmosis membranes were first designed for. But over the past several decades, we've also been able to do the same thing, but from municipal wastewater. So there are several installations of this. One of the best known is in Orange County here in California. But there's a wastewater treatment plant, and right next to it, a drinking water treatment plant that takes the wastewater and turns it into drinkable water. And the regulations are so strict on it, but it leads to that water that comes out is cleaner than what comes out of a drinking water treatment plant. So there's a case of circularity that works out really well. Another example would happen actually in some of these mining installations, right? It's like you get some tailings and then you say, oh, let me recycle that, like make a recycle stream and push it back through and see if I can get more. So we do this all the time when we have what's called single pass conversion going through a process, and we say, oh, but if I turn it back and have it go through multiple times, I can get a higher efficiency from it. So an example of this is like taking a nickel and cobalt solution that's produced when you're manufacturing batteries and saying, oh, let me get that back because then I can increase the purity of my nickel and cobalt generation. So there's a huge case to be made here in saying to companies, hey, what if I could get you some of your precursor back? Would you be interested in that? And then you might not even have to pay a wastewater treatment plant to take it as well.
Sounds like a huge economic opportunity. Another example I can think of is lead acid batteries. And
yeah, great example.
Virtually anyone who has a car, even an electric car, has lead acid batteries. And there, I believe we have close to 99% recycling rate of lead, which is hazardous for mining. But now we don't have to mine very much lead because most of the lead are circular. In contrast, for lithium-ion batteries, I think our recycling rate are just around 1%. So there's a lot of room for improvements. And I think there's the promise of circularities for a lot of these solutions that we need for sustainability. So we're coming to the end of our time here. I want to make sure we have time to answer some questions. So let me hand it off back to Anita to field a few questions from our audience. Anita.
Yeah, we've got some questions coming in from the audience. You kind of touched on this, but maybe you could go a little bit further on the role of water in chemical manufacturing, specifically of fertilizers and fuels. And then I think what's also fascinating about what the both of you are talking about is the different disciplines, professionals that are needed in the entire supply chain when we talk about circular economies. But if you could talk about the role of water in chemical manufacturing a little bit deeper with regards to fertilizer and how that fits into the entire supply chain.
Absolutely, yeah. So when it comes to fertilizer production, a fair number of fertilizers are actually sold in liquid form, right? So they are dissolved in water, and then a farmer will take them and dilute them further. And so that water has to be introduced into the fertilizer production plant at some point. Another example would be when even solid fertilizers are produced, like urea or ammonium phosphate, monoammonium or diammonium phosphate. They have to be precipitated out in some solution, and that is usually water. And so that water is used and then maybe discharged to a wastewater treatment plant. Another place that water is involved, not necessarily in fertilizer manufacturing, but certainly in the fertilizer cycle, is what we call fertilizer or agricultural runoff, which is when it rains on a fertilized field. And a lot of the fertilizer that's not yet taken up by plants goes into rivers, streams, and lakes. In terms of the other question about, what was the other question, Nita, about circularity? And
well,
I might have missed the second part.
There you go. No, you kind of described it, throughout the entire supply chain.
Yeah. Mm-hmm. Yeah, I think there are opportunities for circularity throughout the supply chain. So one example is one of my students works a lot on these lithium selective membranes. And you could think about this throughout the energy storage supply chain, if you will. So it could be in the mining in terms of, can we use things like oil and gas brines or geothermal brines to produce lithium? It could be used in the actual batteries in terms of separators within batteries. And then these lithium membranes can also be used for battery recycling. So similar techniques, similar materials, but they're used literally throughout the whole life cycle of making raw materials for batteries, turning those into actual batteries, and then doing something useful with spent batteries at the end of the life cycle.
Very cool. Well, we have come to the end of our time together. And I want to thank both of you for your time today. And I am loving your course and the what I'm learning about the water cycle and the opportunities and business opportunities that I think a lot of people aren't thinking about. And then also, how can we bring this these new ideas to places around the world where water is far more scarce than in many places here in the United States. So I want to thank both of you for your time today, and the audience. Thank you for joining us today in this special webinar. And as you can see on your screen, if you would like to learn more about the Energy Innovation and Emerging Technologies program and the courses, there's a URL there, a link that you can select in the resource box. And with that, I want to thank both our professors today and all of you for joining us. It has been a pleasure, and we wish you a great rest of your day. Thank you for coming.
Thank you, Anita. Thank you, Will.